So we see, for example, in this image, the part of the fuselage structure. Now I hear myself. A part of the fuselage structure from a 787, I think it is. And you see, like, this is the skin and the specimen, the stiffener that we have in the center, that in this case would be subjected to compression loads. So as we said, the issue that we have with this topic is that delamination, and in particular skin stringer separation, is very hard to predict and is a common failure in these structures. It's very critical, and one of the reasons in the compression regime is that there is a mismatch in the flexural stiffness from both components, and the interaction between that, the large displacements, and if we have an initial damage, makes it difficult to get what's going to happen with this structure. There are different approaches to understand this. We can use numerical simulations, we can use experiments, and for
Yeah, let's see.
Excuse me, we can't hear the voice.
I think it's on now, no?
I don't know if I hear.
But that's the audio, I think.
No, I think. Can you hear now?
Yes, we can hear you now.
But we can't see the presentation.
Okay.
So we use finite element models. We can use LS-DYNA, especially for impact simulations, but this work is all done with the Abacus code. And we also use a trick that we have up our sleeve, that instead of using the graphical interface, we have Python scripts that we developed within QDEL, within a group, to be able to generate the input file directly, what would be the traditional like Nastran file back in the day. So we have consistent known numbering. We know exactly the thickness of our elements, the sizes, and that gives us more consistency when we're analyzing this type of structures. And then I'm going to show two different models of the D. First, like a preliminary model without any Teflon, without any allowing delamination between the stringer foot and the skin. And it's faster to develop, it's faster to run. And it gives us the first set of data, which is the sensitivity of imperfections of our panel, the pre-vacuum stiffness, the post-vacuum stiffness. And then with that, once we know that data, we refine the model. We make the mesh way finer, which is the one here. It's not that the specimen is black, it's that the element sizes are so small that you just see the lines, you don't see the elements. And that's the one that first we'll check with the previous model that we're getting results that we're expecting, and then we can understand how the delamination will begin to propagate, how it does, and how the components behave. So for the first model, as I was introducing earlier, we want to assess the stiffness before vacuum to understand how sensitive the panel is to initial imperfections, and also get the vacuum mode, the post-vacuum response of the specimen, so we can then be sure what we're studying with the next finite element. The mesh is done with continuum shell elements. You can use normal shell, what is called S4R.
Excuse
That
me.
with continuum
Hello?
shell, we take into account the thickness. Hi. Not hearing it.
We can't see your presentation. That screen presentation we are not able to see.
They are not able to see
The presentation. We can see you standing there, but we can't see the presentation.
The window, no?
Yeah, that one, and then it's yeah, that one.
Oh, it's
Yeah.
Yeah, now we are able to. Now we can see. Thank you.
Okay. So for the mesh, we use continuum shell elements. As a reference, this is around 36,000 elements, which seems a lot, but you'll see later what a lot really is. We have a size of 1 millimeter for the free length, which is where we are really studying the response. But for the tap regions, this we can see where we add the resin blocks. We just impose we constrain the degrees of freedom. So on one of the sides, we restrain all 6 degrees of freedom, and then where we apply the displacement, we restrict all the other 5, and we just let the axial displacement. The skin stringer interface is modeled just as a type. So we are not studying the lamination, and we perform 2 sets of analysis with this. We do a linear eigenvalue analysis to get the first 4 backtilt bonds of the structure.
And then we also do a dynamic implicit in compression with a static application to understand the with and without initial imperfections from the eigenvalue analysis to understand how it behaves. All our analyses are running a high performance cluster that we can just leave the models running there and forget about it and come the day after and get the results. This was done with 16 processors, loop parallelization, which I'll explain a bit later on how that affects. And we are getting an average CPU time for the dynamic implicit analysis of 31 hours, which if you divide by the 16 processors, it means that we are getting the results within 2-3 hours. We have the results from these models. So from the backlink analysis, we get the first 4 modes. We see that they are, especially these first 2, quite close in force and displacement. So it would be easy that either one or the other develops. With just a minor initial imperfection from the panel, you could get one or the other. And then we get the other 2 modes with that already with 3 half waves per each of the sides of the skin, one symmetric and the other one symmetric. Now, first we do the dynamic implicit analysis without any initial imperfections. We just take the panel and compress it. Here we see the response. So around the 5 kilonewtons, we get the backlink mode, which we see that we get the asymmetric one instead of the symmetric that we would have expected initially. And then this progresses, and we take it to a load of around 30 kilonewtons, more or less. And then for the next one, to see how different the specimen would behave if it developed another backlink mode, what we applied is the imperfection from mode 1, which was with 2 half waves per side, but the symmetric configuration. And we see that the response is virtually similar, except for the backlink shape. The first displacement response is very similar to what we got from the other. Now, we complicate it a bit more, and we add the cohesive elements between the stringer feed and the skin. Again, one of the advantages that we have with the Python script that we have is that we can implement 0 thickness cohesive elements in there. And what that means is that we are not displacing the skin from the string. We're just taking that as if it was the interface properties. In order to be able to add the cohesive elements, you need to refine the mesh size because you need a certain number of cohesive elements in the crack propagation zone to get accurate result. So that means that we reduce the element size to 0.3 at the interface. And that means that the number of elements that we have in our model now is more than 16 times what we had in the previous one, with the computational costs that entails. So it was 36,000, now it's almost 500,000 elements just for the shell elements. But then we also need to add almost 125,000 for each of the elements that are in the interface. And the way we model the delta is just by not modeling cohesive elements there. So in this location, both the skin and the stringer feed are separated. We do have to apply a contact condition, so with the penetration, the normal friction coefficient that we get in this type of composites. And it's also important to note that we are not studying material damage. So we are not enforcing any hashing criteria, chai wood, chai hill. We just want to check what happens with the damage. The type of analysis is the same that we did with the model without test node. So it's dynamic implicit, no initial imperfections. And in this case, we had to increase the number of processors, which just 16 was enough. So we went to 32 processors, the same parallelization strategy. And now the CPU time went up 6,350 hours, which is 260 days, I think. Again, as we are using more processors, in the end, I think it was around 10 days for the analysis to be compute. Quite a bit time to wait. And in particular, because it was different with the previous one, the cohesive elements, again, zero thickness that we can implement only because we are using that Python script to edit the input file directly. the elastic properties these ones, density, the traction properties, maximum stresses, and the damage propagation. The damage initiation is with the quads criterion from Abacus, energy-based damage evolution, and for the mixed mode behavior, we have this tensioner Kenane that is very commonly used for this type of things. The properties we took were from this paper that was published. And this is the result, the force displacement result from this analysis. Now I put these values here, I will go over it now. So we get an initial stiffness of almost 70 kilonewtons per millimeter, which is very close to what we got from the previous model without the cohesive elements. And then to study how the skin and stiffness separate, we look at a few different events. First is the delamination onset, which is when the skin and stiffness begin delaminating. For the numerical model, we get a bit over 20 kilonewtons. So we are looking around here. Then the delamination propagates, and at some point, the delamination propagates enough that it reaches the opposite stringer foot, the opposite where the initial deform was, and that happens at around 26 kilonewtons. Then after that, it will keep propagating, and if we had considered material failure, there would be, after this, there would be the specimen collapse, but we are not interested in that for this project, so that's why we decided to leave it. So this is a bit how the model behaves. Here on top, we get the interface between the skin and stringer. So blue means that it's still joined. This slight gap that we see here is the location of the insert, and we see that we increase the load. These are the out-of-plane displacements as seen from the skin side. So we increase the load. We already see that between this image and this one, that there is this halfway that wants to try to propagate under the Teflon insert. At this point, it already has. We see that we already get some red here. It keeps propagating. These two halfways merge into just one, a larger halfway. And then if we continue loading, the delaminated area keeps expanding, and at this point, we're already reaching the opposite stringer. We see that, and that's something that we see later in the experience, but that before the delamination propagates, this halfway has more of a straight line around here, and then we see that it becomes like more round. At some point, this is the last point where there is still the stringer and the stringer and the skin are still fully attached. And then at this point, the delamination gets propagates, and we get what is called the tax. So if we had considered in this model, if there was material failure, at this point, if that state of the delamination, the specimen will have already produced. Now, this is a comparison of the numerical results. So we get the green curves are the one that we took from the initial model, different cohesive elements, and these are the other. This is the other model that I'm showing. So stiffness values very close together. Backing load is slightly over 5 kilonewtons, but we see that the lamination, even when we had an initial lamination that did not begin propagating until 20 kilonewtons, which is almost 4 times the baffling load that the panel would normally be designed for. And yeah, 264 days too. So now we have the numerical analysis that we do before the test. Now we want to see how accurate they are by doing experimental calculation. And you saw earlier with Professor Pisani the image of the lab. That was my home for about a month and a half with the manufacturing preparation and all of that. So I'm not going to go a month and a half on what I did, but I'll show you a bit. So the manufacturing of these specimens first begins with the cutting of the plies. We cut the plies, we store them in the freezer because if you leave them out, they become tacky. And then we begin with the mold preparation. This is the plate we have. To clean it thoroughly, apply a few layers of marble coat so it doesn't get stuck there. And then we carefully and slowly begin building up our layer. This pink foil that we have is called the debulking foil, which is used to progressively compress the to progressively develop the plies. So the rule of thumb is for every ply you lay, you usually leave 3-5 minutes of full vacuum. 1, 2, close the foil, apply vacuum through this nipple, and then once we're done, lift it up, lay a few plies again, once we're done with the layup of the skin, we use, you see these blue tapes around, that's what helps us mark where we want everything. So these two come out here, are the ones that we use to insert them. So we lay, probably you cannot see that well, but there is a slight differentiation in that. That's a really thin Teflon film that we put. It's 50 microns, which is what's recommended for also the senior specimens and such small coupons. Then after we put the Teflon, we put the stringer mold, and we begin with the layer of steel. This would be the stringer plies already laid, and it's time to change all the coils and everything we have for preparing for the oven. It has all the different blankets that we need to put, so the field dye, the PET foil, well, and for manufacturing. This is a wonderful autoclave that we have in NMCAD Delft. So also, as with the numerical analysis, we put it in there at night, we come the day after and our cake or specimen is baked. And now begins the preparation of the specimen itself. Once it's fully cured, we take all the measurements, we make sure that the specimen is up to the standards that we're expecting, cut it, weigh it, measure it, and then we do the resin tabs that we saw earlier in the presentation. This is again made with metal field epoxy that is special for this type of applications. So mix it. We made this mold with wood. We let it cure overnight, and the day after we demold it, and it has to be cured in an oven for 12-14 hours. Once we have the resin tabs manufactured, we have a group of technicians within NMCAD Delft that make sure that with a CNC machine, they machine it. So we have both the upper and lower faces of the tabs. They are perfectly parallel because the specimens like this are very sensitive to not perfectly parallel loading conditions. Once that's done, we paint it white. We apply a few layers of white paint, and then we speculate because we use digital image correlation techniques, and that's crucial for it. And then this is the last step. There are some marks here that we use to align the specimen every time we put it in the within the machine, and we want that the center of gravity of the specimen is exactly aligned with the center of gravity of the machine to reduce any non-axial loading on the specimen. Now, these are the two main machines that we use for the testing. So one is just the testing itself with all the equipment. I'll go over it later. And we also have a system that we use to check if there are initial imperfections on the specimen, if the specimen is perfectly bonded, that there are no voids in there, that there are nothing that we didn't expect, and also we'll use later on when we are testing to track the progression of the delamination. Going back to the testing equipment, this is the test machine, an NDS material testing system that has a load cell up to 500 kilonewtons. We place the specimen. We use two LDSs, one on each side, to check that we are applying the load perfectly parallel and there are no mismatches or rotations in there. We use two digital image correlation systems. This is the one that is looking from the skin side. It's made of two cameras and it's 3D. So with these two images and a calibration that we have to apply before, we can get strains out of plate displacements, in-plate displacements, and that's always really good extra information that we always get. This is the DC to control the machine, and this is what we get from the DSC system. See, this is the specimen that is already trained. Now, tests. The tests were done at a displacement control, 0.1 millimeters per minute. We didn't want the test to be too short because then it's not quasi-static, but we didn't want to last 2 hours. So we were targeting around 15 minutes of testing, which were more or less that. Then, as we said, the laser displacements that not only helps us check whether there is non-perfect axial loading, but also these machines and also the specimen, there is some compliance to it before it really takes the load. So with the NDSs, we attach them to the top plate, and then we measure the displacement of the upper part of this resin tab. So we know that we are actually measuring the actual compression of the specimen, the actual compression. And then, as I introduced earlier, we stop the tests periodically to check how the deformation was propagating as the load increases. So this is the load displacement curve, but this is after there is some slight post-processing. So what we did was, we do always stiffness tests, check that we are the specimen is behaving with what we get from the numerical models. So then we load, and you see that there is a big load from here. That's when the delamination concept happens. So we stop the test here. We retrieve the specimen, we do a C-scan, we check how much the delamination propagated, and then we reload again. The load displacement curve doesn't go on top of it, but rather goes a bit lower and just continues. So what we do is we take for the second test run, we just remove the first part, and SSCS2, so the second specimen was stopped 3 times. Once after the delamination's onset, once here, and then after failure. And for the first one, it was like 8 times, I think, in the end. So I'm going to focus on the second specimen to keep things more simple. We get the 3 events that we're looking for. We check the initial stiffness, the delamination onset, and the collapse source. So, first events. First, we get buffing, which for the experimental specimen happens around 8 kilonewtons. Since these specimens always have some slight imperfections, it's not a perfect 0-1 scenario when you see like the perfect specimen and then the shape just develops. But at around 10 kilonewtons, we can already identify the buckling shape. This is the bit higher growth, around 20. But we see that we're getting the same halfway that tries to propagate under the teflon. This is the view from the spin side. And then, however, from the stringer side, so far we don't see it. With the C-scan, green corresponds to impact material. This black that we see here in between is not that it's damaged, but it's the stringer. The C-scan that we're using works in a water bath. So since the omega is constrained with the resin tabs, no water can get in. So we just see it as a black signal because it doesn't propagate. But what we see here, this is the location of the initial teflon, and we see that it's still at 40 millimeters. Now we continue loading, and we get to the delamination. We load, and at around 26.5 kilonewtons, we just see a load. And what happens is that these 2.5 halfways that we're seeing, just after this teflon opens, turn into one large halfway. And we got a sudden jump of the delamination length from 40 millimeters to 76. So it was quite a sudden increase, unlike what we saw previously in the numerical lab. Now, there is a second event that we mentioned earlier, which is the propagation to the opposite flange. And for us, it happened, cannot be seen that well because the delamination onset was with a low drop of 3 kilonewtons. But this propagation to the opposite side, there is a just minor of 0.1, 0.2 kilonewtons, and a very soft noise that we hear during testing. So it's like, boop. Then we do the C-scan, we see that we already began propagating to this. We see like a half moon shape. So there was a slight increase also on the delamination length on the location of the teflon insert, that we already see that it's propagating to the opposite flange. And as we continue loading at 34.5 kilonewtons. The specimen just collapses. So the propagation goes all the way through, and we see this tunnel from one side and the other. We also see some stringer clipping here. And now, since there is stringer clipping, water can get in the omega, and now we do see the signal. So these are videos first of the delamination. Again. And we see that it's and this is the collapse already. So when you take a look at the frames that we recorded with the video, we see that right before the specimen begins delaminating, there is a small change in the backing shape that it goes from 2 to 3, and then within milliseconds it just begins and the delamination opens. And now the specimen collapses. Yes. So, again. Now, as I mentioned earlier, one of the advantages that we have of using the DSC is that we can see how the specimen behaves and how the outward plane displacements are going. So, the plate again, both from the stringer side and the skin side. Again, the skin side is easier to see how the backing shape changes. It begins to propagate, and suddenly we just get this one big halfway. Now we're looking at the propagation of the delamination, and pay attention to this side, that we see that it's, again, the straight halfway, and then at some point we see that it just develops a more rounded shape. Right. Then that we see it becomes way more round, so it's already propagated. And then for the final part, which is the collapse of the specimen. Now, obviously, when we start loading, it's already loading with this one halfway instead of the two symmetrical that we got before the delamination. So, there you go, the collapse. You see, going against, we have waves here. This is already the stringer foot is buckling upwards, the skin is buckling inwards. And then it just. So these are the postmortem images of the specimens. We see that the failure of both of them is very similar. We get stringer killing, we get the same tunneling between the skin and the stringer. And in the case of in specimen 2, we also saw some fiber pullout. And that when it broke, it just ripped some fibers from the skin. Now for the good part, which is how good did our numerical models compare to the experimental. So we first take this data, obviously like, oh, what's happening here, like they don't match. But that's because we're comparing with the displacement that we take from the machine for the compliance. The moment that we get the load from the machine, that we get the displacement for the NDS sensor that actually measure the compression, we see that we get almost perfect response. The red curve corresponds to the model with the cohesive elements. And although we had the delamination onset for the experiment at 26.5, the one for the numerical model is 2021. I'll go a bit more detail. But all in all, the pre-post buckling response, very relatable. This is a comparison between the numerical models and both specimens. The stiffness values, again, quite close between a numerical model and simulation. The backing load is where there is a slight difference, let's say. And then the delamination onset and propagation of the delamination loads that we estimated from the numerical models are between 15–20% lower than what we get with the experimental results. Now, a comparison between the out-of-plate displacements seen from the skin side between experiment and simulation. The backing shape is virtually similar. We see, again, as we were seeing earlier, the propagation under the Teflon, how it changes from 2 half waves on this side to just one when we have the delamination fully open, and then how it mounts up. This is the once the propagation of the delamination has reached the other foot, and we get the similar rounded shape of the halfway that is trying to go through. Now, to wrap it up, the difference we get between both the numerical model and the experiments that we did. There are some differences. First, we get a slightly different shape after the delamination onset. We see that here is 3 half waves, while here we get just 2. And also the buckling of the stringer foot. In the experiment, we saw that it buckles upwards and the skin inwards. While on this one, in the numerical specimen, probably due to imperfections from the specimen itself, but they both buckle up, which also affects how the damage between the skin and stringer is going to propagate. It's more dominated by mode 2, mode 3, rather than what would be mode 1. Then a few other differences that we saw is that in the numerical model, the delamination propagated smoothly, while in the experiment, it was sudden, always, both for delamination onset, both for propagation to the opposite stringer foot. That there is some sticking. Also, when you manufacture a component like this with a Teflon insert, there's going to be some sticking between the stringer foot and the Teflon. So that means that some energy is built up there, and at some point just releases. That's something that we cannot capture in the numerical model. And now, to conclude, we managed to manufacture and study 2 different single stringer components that gave us information on the response of what would be a multi-stringer panel and on the post-buckling regime. We saw that both from the numerical specimens and the experiments that the post-buckling capabilities of these specimens are enormous, that we were getting always buckling before 10 kilonewtons, while even with the initial delamination, the propagation of that delamination will begin until 26 kilonewtons. That's over twice that load. And we also managed to simulate this response with numerical simulations, having a good correlation between the loads at the delamination onset, albeit, again, between 18–25% lower, but still we're on the safe side. And we believe that these results contributed to understanding better what's the post-buckling response of these panels and enhancing these capabilities. Thank you for getting with us. Yes.
Nice.
Thank you.
Now, we are result. How you decided subset and step sizes? Those are like,
Second,
how do you decide subset and step size in DIC? Because those changes were patterns on this specimen.
I'm sorry, I didn't.
Brings up the speckle density.
The speckle density. Okay, so
Analyze that you divide your image in subsets.
Yeah. So I don't know which DIC system you use. The one we use is from Correlated Solutions, and first it always gives you a suggested set size. So you take that as a starting point. But then one of the metrics that you can retrieve with the digital image correlation is the what they call the sigma pixel, which is the predicted error at that location for the out-of-plane displacements, for strains, for whichever metric you're looking at. So there's a bit of iterative process in there. So we try a subset, we know that we get this error, and then we try to run the DIC again with a smaller one, for example. And then we see if the error increases or not. And the same goes, so it's a subset, and then there is another parameter that you change, which is the number of iterations it does within its subset. And that we also do with a slight sensitivity study. So we start with a high number, then we keep, because the lower you have that number, the longer it takes to compute. So we start with, let's say 8, we compute, we go down to 3, and we know that when you go from 3 to 2 to 1, you get the same result. So we take it at 3.
Participated in experimental and numerical study, you got experimental value greater than that of numerical studies,
Yes.
right? And in your conclusion, we are concluding that maybe due to the experimental one is due to the mode 1. And mode 2 and 3 are dominating, not mode 1. Right? So in that case, can't you impose mode 1 as your imperfection in your numerical model and get the result?
Yes, that would be that. There are a few tweaks that we can do with this model. First would be, for example, getting the actual imperfection from the panel and implementing the imperfection instead of just the backplane shape. That would be one way, and that we can try and see if we hopefully get a.
Normally, if we are not getting the actual imperfection, we do impose the eigen mode as the imperfection, right?
Yeah, but in this case, we tried with applying different imperfections, but it didn't change the way that the stringer foot buckled once it eliminated. It didn't change. So we are talking about this. So no matter which imperfection we apply, the stringer foot always buckled in the same direction that we tried the first 2 modes. Maybe if we went to a higher buckling mode, it would be that. With the first buckling mode that we studied, it didn't affect the buckling shape.
Anyway, we are on the safer side of it.
Where only?
We are on the safer side of it, so it's no problem.
A few questions, I guess, of great presentation. In fact, the work which you have done is very similar to what we do in industry.
Oh.
To everyone's on delamination.
Mhm.
I'll talk about it in my talk post lunch. First question I have is, you talked about the machine complaints.
The machine?
Machine complaints.
Yes,
when you
yes.
talk about post-displacement.
Mhm.
Have you assessed the impact of that on the local deformation mode, which you are saying, not on the post-displacement, but because the boundary conditions will be different, because you have a finite stiffness compared to probably what you have on the FEA now. Have you accounted that in the simulation?
No, but I'm not.
But that is extremely important. We have seen that in the industry.
Yeah.
Extremely important to tailor the stiffness, the boundary stiffness. And we have seen very different results, especially probably what you talked about, the out-of-plane deformation direction. So generally, another thing you talked about the mesh sensitivity or the sensitivity of the speckle pattern.
Yeah.
I hope you probably might have done the mesh sensitivity here in this case to bring the quantity of interest locally with sensitivity of
Yes.
was it done?
Yes.
Probably I think sensitivity or the machine stiffness.
Thank you very much.